we will start the third week of this course. So, in this third week, I will start talking about the concept of symmetries in crystals, and the topic of symmetries in crystals will also be continued into the fourth week. So, we will start the topic of symmetries in crystals, and in the first part, that is the third week, I will be talking mainly about point symmetries. So, let's talk about symmetries in crystals. So, in crystals there are two kinds of symmetries. Okay, there are the point symmetries, okay, and these are similar to molecular symmetries that you might have encountered in a course on group theory. In crystals there are additional symmetries called translational symmetries, okay, which are very specific to crystalline solids, okay, and we will talk about both of these in more detail. So, the point symmetries, as I already said, they are similar to what you see in molecular symmetries. Okay. So, there are rotations, reflections, inversions, and then there are combinations like rotations and inversions, so roto inversions, and then there is roto reflections. Okay. Now, conventionally when we are talking about molecules, we do not usually talk about roto inversions, we talk mainly about roto reflections. Sometimes they are referred to as improper reflections. In crystals, it turns out that roto inversions have been used conventionally. The translational symmetries are specific to crystalline solids and they do not exist for molecules, and these include things like glides or glide plane and screw rotations. Okay, these are very specific and we will see these in more detail. Now, what is a symmetry? A symmetry is an operation that leaves the crystal, and you should keep in mind that it is an infinite crystal and it leaves this crystal unchanged. Okay. So, it is some operation. So, for example, rotation is an operation. So, rotation about an axis, okay, reflection about a plane, inversion about a point of inversion, okay, and so on. And what is important about symmetry is that it is these symmetries that are used to define the crystal systems. So, when you say a crystal system is cubic, you mean that it satisfies some specific symmetries. Okay. So, now Now we will first talk about the point symmetry elements, and as I had said, these are similar to those seen in molecular symmetries. In fact, they are identical to those seen in molecular symmetries, and the point symmetries, when you learn molecular group theory, you learn that these symmetry elements all pass through one point in the molecule. Okay, so that is why they are referred to as point symmetries. Okay, and we will just use that same terminology. Okay. So, what are the different kinds of point symmetries? Okay. Now, whenever we are discussing symmetries, there is a concept of a symmetry element. Okay. So, symmetry element and this symmetry element leads to a symmetry operation. So, we always talk about symmetries in terms of both symmetry elements and symmetry operations. Okay. Now, what are the symmetry elements and symmetry operations? So, a symmetry element, a point is a symmetry element, okay, and what is the symmetry operation that is possible if you take a point as a symmetry element, and the only symmetry operation that is possible is a center of inversion. So, if that point is a center of inversion, then the operation is actually inversion, okay, and I am emphasizing the center because you are inverting about the center. Okay. So, its inversion about the center is the operation for that symmetry element. Then you could have plane. Plane is a symmetry element, and a plane, the operation that is carried out by the plane is a reflection about that plane. So, you reflect the entire system about that plane, and you will get a new system, and this is the symmetry operation that is carried out by the plane. Then you could have a symmetry element that is a line, okay, and you could do a rotation, okay. Sometimes it is called a proper rotation in especially in molecular group theory. So you could rotate the entire system about that line, okay, and in that case the line will be called the axis of rotation. You rotate by some number of degrees, so you have to specify by what amount you do the rotation. Now a line can also act as an axis for a rotation followed by a reflection, okay, followed by a very specific reflection, and we'll see this in more details. These are referred to as rotoreflections, or sometimes they are referred to as improper rotations in molecular group theory. The line can also act as a rotation plus followed by an inversion, okay, that is called a roto-inversion. This is also another common operation, especially in crystals. It is roto-inversions that are more commonly used. So these are the point symmetry elements, and these are the various symmetry operations that we will be talking about. So and usually the way to learn symmetry is through simple examples, okay, and we will illustrate this, okay. We will illustrate this for we will now illustrate some simple through simple examples. We will illustrate the symmetry operations relating to rotations and reflections, just the proper rotations and reflections. So let us go to rotations, okay. This is a point symmetry, and we are specifically in this case we are referring to proper rotations. Proper means rotation without any reflection or inversion, okay. Now let us take an example and let us take a typical tetrahedron like a silicate. So let us say if you have a silicate tetrahedron, so you have a silicon atom at the center and you have oxygen atoms forming a regular tetrahedron. So you have 4 oxygen atoms forming a regular tetrahedron, and this is coming outside the plane of the paper. So I am showing it in dark, this oxygen, and this is going behind the plane of paper. So I am showing it in dashed line. Okay, so this is a silicate, this is tetrahedron. Okay. Now if you imagine taking an axis that passes through the silicon and one of the oxygen atoms. So for example, if I imagine taking an axis that passes through this silicon and this oxygen, so it goes through this silicon oxygen bond and it goes all the way through. So just extend that axis all the way around. Okay. Now you can see that this axis, okay, is a symmetry axis, for a rotation. And it's a rotation, it is a symmetry axis for rotation by, and its rotation by a specific number, rotation by 120 degrees. Okay. So if I rotate, okay, and I should usually we follow the convention that the direction of rotation should be counterclockwise. So if I rotate by 120 degrees, okay, then you can see that when I rotate by 120 degrees, this oxygen will go to this oxygen will come to this oxygen will come to this, and essentially you will get a structure that is identical. You will get a structure that looks identical to the original silicate structure. Okay. So that is what happens when you do a rotation by 120 degrees, and you can see that once you have rotation by 120 degrees, then you automatically have, it automatically implies rotation by by 240 degrees, okay, which is same as twice you do the rotation by 120 degrees. So, you rotate by 120 degrees and rotate by 120 degrees again, okay. That would also be a symmetry operation, and let me show this in a slightly different color. So if I rotate by 240 degrees, then this atom will go all the way to this atom, okay. Similarly, this atom will come all the way to this atom, and this atom will rotate all the way to this atom, okay. So, that is what happens when you rotate by 240 degrees, and if you do it 3 times, okay, 120 into 3 equal to 360, okay. And so, what this says is that if you do this rotation operation 3 times, then you get back the original structure, and there is no change from the original structure, okay. So, this axis is called a threefold axis of rotations, okay. And we will see later on that there are two notations. We either call this symmetry as Cn, okay. This is in the molecular notation. This is molecular or Schoenflies notation. Schoenflies notation. This is very common in spectroscopy, or we will just call it 3 in terms of in what is called the Hermann-Mauguin notation. Okay. So, usually crystals have several axes of rotation and several symmetry axes. So, just an example, if you take a cube, so if I take a cube, then you can see that it has several rotational axes, several axes of rotation. So, if you take a cube, you can imagine that I'll draw a few axes of rotation. So, if you take an axis that goes this way, goes through the crystal, comes out from the other side and comes here, okay. So, it goes through the center of this crystal. You can see immediately that for a perfect cube, this is a C4 axis, okay. So, if you C4 means a C4 axis means you rotate it by 90 degrees, okay. So, the way to think, if you have a threefold axis of rotation, then the rotation by 360 divided by 3. So, just keep in mind, in that case we saw 360 by 3 equal to 120. So, if you rotate by 120 degrees, you get a symmetry operation in this case for a threefold axis. In this case, you rotate by 90 degrees, okay. So, if you rotate by 90 degrees, then you can see that this point will go to this point and so on, okay. So, the crystal the cube will remain unchanged for rotation by 90 degrees, okay. So, if you rotate by 90 degrees, you still retain the cube about this axis, okay. And since you can rotate by 90 degrees, so 90 degrees rotation, you can also rotate by 180 degrees, that is twice 90, or you can rotate by 270 degrees, that is 3 into 90, and if you rotate by 4 times 90 degrees, you get 360 degrees, which is back to the original structure. So, these are the various symmetry operations that you get from this symmetry element, from this C4 axis, okay. Now, you can also have a C4 axis like this, passing through this face. Okay, so this is another C4 axis. Okay, and you can have a third C4 axis passing through this face. So you come this way, it goes through, and it comes out from that side. Okay, so you could have these 3 C4 axes. Okay, so this is also a C4 axis. So it basically goes through the center of one face, and it's perpendicular to that face. So these are all C4 axis. Now it turns out that a cube also has some C3 axis, and these are slightly harder to see, but not much more difficult to see, and I will show them in this violet color. Okay, so suppose I take an axis that starts from one corner, goes through the body diagonal, and comes out from the other corner. Okay, again it comes out from the opposite corner along the body diagonal. So you have an axis that starts at one of the corners, one of the edges of the cube, goes along the body diagonal, and comes out of the other edge. Okay, so this is what we are saying. Okay, and this axis, okay, probably better to show this in dots. So let me show this way. Okay, so it goes through the center of the cube. It goes through the center of the cube and comes out from the other side. Okay, so this is an axis, and you can see that this is actually a C3 axis. C3 axis, that means it's a threefold axis of rotation. Okay, and again it's I mean this is slightly harder to see, but not that much harder. Okay, you can you have to visualize this, okay, by actually taking a cube, but what you will find is that you will have these 3 points, okay, turn into one another during this rotation, and these 3 points go to another. Okay, so again it's not I'm not going to demonstrate this, but essentially you can see that this will permute 3 points. Okay, so I'll just show you. So if you do this rotation, then these 3 points will go into each other. So if you rotate by 120 degrees, this point will go here, this point will go here, and this point will go here. If you do it again by, and similarly these 3 points will also get permuted. The opposite 3 points, I will show that in a different color. Let me take light green. So if you do by 120 degrees, the back corner and this point will get permuted into each other. Okay, so now you can immediately see that there are 3 more C3 axes. So there are total. So a cube has 4 C3 axes, because you can start with any corner and go to its opposite diagonal. Okay, so there are 8 corners in a cube. So there are 4 C3 axes, and we already saw we have 3 C4 axes. Okay, so this is what characterizes a cube. Okay, now one of the things that you will notice is that if you had a C2 axis, okay, so we notice that C4 also generates 180 degrees, and so we see that C4, if you do it twice, so I write it as C4 square. So you do the C4 operation twice, you get a C2 operation. So if you do 90 degrees and 90 degrees, you get 180 degrees. 180 degrees is 360 divided by 2, so that's a C2 operation. So the symmetry operation C4 square is same as C2. Okay, and so when you a C4 axis includes in it a C2 axis, you could have additional axis that is a C2 axis but not a C4 axis, and that is also possible. Similarly, if you had a C6 axis, that would include a C3 axis. A C6 axis would contain in it a C3 axis, would contain in it the C3 axis. So we will have C6 twice is nothing but C3. Okay, this is a general property, and you can see this. You can do this by just by looking at the rotations. Okay, now the most interesting thing about crystals is that the crystals, it is required that crystals should fill space. Okay, so since crystals are required to fill the entire space, there are restrictions on the kinds of axes that you can have. Okay, so and let me emphasize this. So I'll choose a red color just to emphasize this. So and I'll write this here. So only C2, C3, C4 and C6 are allowed. So for crystals, these are the only rotational symmetry axes that are allowed. Okay, so you can have a C2, you can have a C3, you can have a C4, or you can have a C6. You cannot have a C5. Okay, and the reason you cannot have a C5 has to deal with the fact that if you have a C5 axis, then you would have something like a pentagon, like a regular pentagon. Okay, and if you have a regular pentagon, okay, you cannot fill space with regular pentagons. Okay, so this is a restriction again that has to do with the it goes back to the crystal systems that are allowed and the types of Bravais lattice that you have. So since the crystal has to fill the entire space, it cannot have a C5 axis, and this is a very interesting property that a perfect crystal cannot have a C5 axis. Okay, so that itself is a very interesting point. Okay, so we said that only C2, C3, C4 and C6 are allowed, and the reason is that if you have a C5 not allowed, and the reason for that is that if you have a C5 axis, okay, then if you let's say I had a C5 axis coming out of the plane of the board, okay, then around the C5 axis there would be something like a pentagonal symmetry. So if you have a 5-fold axis of rotation, then there should be some sort of pentagonal symmetry, 5-fold symmetry around this, and so your unit cell will have something like a pentagon. And if you take pentagons, okay, so pentagons cannot fill space. So suppose you take a set of pentagons, okay, again you can see this. If you try to fill space, okay, if you take perfect pentagons, these are all regular pentagons, okay, so the angle is 360 by 5, sorry, not, okay, so they have the exact angle of the pentagon, that is 108 degrees. Okay, and if you take a regular pentagon, okay, so it is 108 degrees, okay, is the angle of a regular pentagon. And if you just take regular pentagons, okay, and you try to fill space, okay, then you will always get some voids. So if this is 108 degrees, this is 108 degrees. Now if I put another 108 degree here, okay, you can see that 108, 108, 108, okay, and you can see that this angle is going to be 360 minus 3 into 108 is equal to 36 degrees. Okay. So, what that means, and you cannot have a 36 degree angle in a pentagon. So, there would always be some empty space. Okay. So, pentagons cannot fill space. Okay. And in fact, this is why you never have five-fold axis in crystals. Okay. Now, it should be mentioned. Okay, I will just mention this, that in around 1980 there was the discovery of these special crystals. They are not real crystals, they are called quasi crystals. Okay. And these are not real crystals, but these appear to show five-fold symmetry. Okay, so quasi crystals, they appear to show five-fold symmetry, and the discovery of quasi crystals. Okay, so the quasi crystals were discovered in 1981. So they were discovered in 1981 by a scientist whose name is Daniel Schechtman, and Daniel Schechtman was later on awarded the Nobel Prize in Chemistry. So he was awarded the Nobel Prize in Chemistry in 2011. Okay. So, but essentially these are not perfect, these are not crystals in the usual sense. Okay, they are referred to as quasi crystals. Okay, and I mean you can read about them in various sources. We won't be discussing too much about quasi crystals, but they essentially show this five-fold symmetry, okay, which is absent in regular crystals. As far as regular crystals go, the only axes of rotation that are possible are 2, 3, 4 and 6-fold axis. So, in this lecture I have talked about symmetries of crystals, and in particular I focused on the rotational symmetry. So, in the next lecture I will look at the other symmetry elements of a crystal, like reflections, inversions, and then we look at roto reflections, roto inversions, and see the standard notations for these operations. Thank you.